Welcome to Mrs. Neller's notes for her double block algebra class. These are the notes for section 8.7 entitled Exponential Decay Functions. And today we're going to take a look at an exponential model to solve word problems that deal with exponential decay. So in the previous sections of notes we talked about exponential growth. Now we're going to talk about exponential decay. And actually, I see a typo right here. This is supposed to be exponential decay. And that is when a quantity decreases by the same percent for each unit of time. So when we were graphing a few sections ago, the base on your power would stay the same, but the exponent would change by 1 unit. And when that happened for a decay function, you could see the graph going down over each unit of time. And it would go down really fast for exponential decay. So the equation we're going to work with today is the same as what it was yesterday, except for one minor change. We're still going to have our initial amount, and we're still going to have our rate, and we're still going to have to write it as a decimal, and we're still going to have our time. But the thing that changes in the equation for today is that it's no longer a 1 plus r, it's a minus. So that's the difference between the exponential growth and the exponential decay. And there are a lot of real-world examples of exponential decay. Bacteria and viruses, once you start to take medicine, that medicine makes their growth decay. That's how the virus and bacteria go away and you become well again. Populations can decrease if people move or get sick and die. Interest payments can decrease over time if the interest rates go down or you start paying them. Radioactive substances have a half-life, so they are constantly decaying. Um, Basketball tournaments, when you have like elimination rounds, could be any kind of tournament really. Endangered species, if there's certain animals that are not reproducing and not growing, or there's a lot of human activity that is killing them off, they can show a decay model. Or vehicle depreciation, or like electronic depreciation. If you buy a new computer, after a few years it's not worth as much anymore. Same for a car. Once you drive a car off a lot, they say it decreases by half. Okay? So those are just some examples. And we're going to take a look at some in a couple word problems, and then we're going to do a graph as well. And this first problem here, they just want us to write the equation, so we're not going to actually solve it. We're just going to be looking for those key pieces of information. Okay, so we're still going to be using the y equals c times 1 minus r to the t. So today we're subtracting the 1 and the r. So you have a $35,000 car, and it depreciates at a rate of 8% each year. So this $35,000, that's your initial amount. And the 8%, that's going to be your rate. And they just tell you each year, but they don't tell you how many years this is going to go on for. So when we write our equation, we'll substitute in the 35,000, and then we'll do 1 minus our rate. Now remember, we have to change this to a decimal, so we have to move our decimal 2 places, 0.08. And then the time, we don't know. We don't know how long this goes on for. We don't know how long you have the car for. So we'll just put t for time. And we're going to simplify this just a little bit more by subtracting the 1 and the 0.08. So this would simplify into 3,500 times 0.92 to the t power. So that would be your function for this situation. Okay, for part B, you have a stock that's valued at $250. Then the value decreases by 4% per year. So again, we have a initial amount and we have a rate. Whoops, that's R, not T. But they don't tell us how many years this is going to go on for. So we'll have y equals 250 times 1 minus, now 4% as a decimal is going to be 0.04 to the t for time. Again, we don't know how long you have this stock, so we can't put in a number for t. But we can subtract the 1 and the 0.04. Now, a helpful hint when you're dealing with these decimals, always think of this 1 as like 100, and then just kind of ignore this little decimal place here when you're subtracting. So think of this as just like 0.04. So you've got 100 and you're subtracting 4 is 96, and then make it 0.96. So this will be our model for this situation. So just like when we were dealing with exponential growth, we're still looking for those 3 key pieces of information. Now in example 2 here, and example 3, we're going to have some problems where they want us to actually go through and solve. They're going to tell us the time as well, so we can substitute that in. So for example 2, you buy a used computer for $400. The computer depreciates 5% per year. Find the value of the computer after 7 years. So we're still using our generic equation here. 1 minus r to the t. So we're going to look for our initial amount, which is C. So that's our $400. And our rate is the 5%. So we'll make that a decimal. And then we have 7 years for our time. So as you're reading these problems, if you want to highlight or circle or box in those 3 key pieces of information, do that. So we'll have 400 for our initial amount. And we're going to change the 5% to 0.05. And then our time now is 7. So we have an actual number we can substitute in. Now we're going to simplify this. Think of this as 100 minus 5. So that'll be 0.95 to the 7. So we want to simplify that first before we plug it into our calculator. Remember, just like the previous section of notes, we're just doing the 0.95 to the 7th. Don't do the 400 times the 0.95 because that's going to change the base. That changes the number that you're raising to the 7th power. We just want the 0.95 to be to the 7th power. And then when you put that into your calculator, remember this is money, so you should get $279.33 when you round to 2 decimal places. Okay, example 3 is another word problem. It's a little bit longer. And this time they kind of give us part of an equation here. It says the amount of aspirin in a person's blood can be modeled by this equation right here. So I'm going to write that down because that's probably the equation that we're going to be using for this problem. So it's very similar to the one we've been using. Instead of a C, they have an A. And I tell you that A represents the dose of aspirin. Okay. And then we have 0.8, so it's kind of like they've already done the 1 minus the rate for us. And then we have T for time, probably. It says T represents the number of hours since the aspirin was taken. Okay. So right here they tell you what A represents. A is the dose, and then T is the number of hours. So our last sentence here, find the amount of aspirin remaining in a person's blood for a 550 milligram dose after 5 hours. So there's my initial amount, and there's my time. So I'm going to substitute the 550 in for A, and then the 5 for the T. And again, I want to do the 0.8 to the 5 first, get an answer, and then multiply by the 550. And we can still round to 2 decimal places here. So we have about 180.22 milligrams. So make sure you label it, and then if you wanted to write this as a complete sentence, you would say the amount of aspirin remaining in a person's blood after 5 hours is 188.22 milligrams. So in your homework for tonight, you might see more of these modified equations where they're giving you a similar format, but they're giving you a little bit more of a structured equation to start with, and then you still have to find a few pieces of information to plug in. But it's going to follow a very similar pattern to the exponential growth and exponential decay equations that we've been working with. Okay, now in example 4, now that we've seen both growth and decay, there's a way that you can just look at an equation and know if it's going to be growth or decay. And the way that you can do that is you have to look at the base. The 3 and the 0.75 and the 4/3. If you look at just that number, it will tell you if that equation is going to be growth or decay. Now, in class, we'll probably do a little experimenting with these. We'll probably graph them on the graphing calculator so you can see what happens. And this first equation, the y equals 0.55 times 3 to the t, that will be a growth function. And this next one in b, y equals 2 times 0.75 to the t, that's going to be a decay function. Now, just based on that observation, you should be able to notice that when this number, the base, is a number bigger than 1, it's going to be a growth function. And this number here, this is a decimal, 0.75, it's less than 1, so it's going to be a decay function. So then 4/3 is like 1 1/3, so that's more than 1, so that would be growth. And the reason we've picked 1 as our cutoff is because the base can't be 1. When we were dealing with graphing and first talking about exponential functions, we said that that base couldn't be 1. It had to be a number greater than 1. Okay? So if your number, let me write that down, is greater than 1, it's going to be growth. If your number is less than 1, it'll be decay. Okay, so that's like a little symbol there to remember that. All right, for last example here, example number 5, we're going to graph. And before we even graph, I want you to look at the base and tell me if it's growth or decay. So look at the 0.9. Don't worry about the 5. Just look at the 0.9. That number is less than 1, so this should be a decay graph. So now we'll make a table of values and we'll graph it and we'll make sure that it actually is decay. And we're going to pick some numbers that are negative and some numbers that are positive, just like we did a couple of sections ago. Now this one you probably want to do on your calculator, okay? So do 0.9 to the -2, get an answer, then multiply by the 5. And you should get 6.17. For the -1, when x is -1, or whoops, technically it's a t in our function. So when t is -1, we'll have 0.9 to the -1, get an answer, then multiply it by 5, you get 5.56. Now for 0, remember anything to a power of 0 is 1, so 0.9 to the 0 is 1, times 5 is 5. Notice that our numbers are going down here, so that's good. That means that it's representing a decay function. Okay, 0.9 to the 1 times 5 will be 4.5, and then 0.9 to the second times 5 will be 4.05. So our graph's not going to decrease super, super fast, but it's still decreasing. So a little bit beyond 6, -1, 1, 2, 3, 4, 5 and a half, roughly, 0, 5. And then we'll have 4.5, and then just a little bit above 4. So this is kind of what our graph looks like here. So it is going down from left to right. So it is decay, but it's more of a gradual decay, and that's because this base is so little. If we had a bigger base, then it would decay a lot faster. So now that we've seen exponential growth and decay, we've seen them graphically, we've seen them in equations, we know how to compare them back and forth. These are what you need to be practicing and looking out for and making sure that you understand in this practice set of homework problems. So make sure you show all your work, make sure you have some graph paper, and if you have any questions, stop on in and see us before school.